And I again want to thank the organizers for having me here and be able to tell you a bit what we're doing at PITC in integrated photonics, although you heard already about it. But you also heard a bit about open innovation already. And I'm very happy to say that we're now doing and practicing this already for 20 years very actively. And like everything in Eindhoven, it started, of course, with Philips, who 20 years saw that closed collaboration in a closed campus didn't work anymore. And they really ignited a wave of open innovation in what is now called the Brainport area. And one of the things they also said when we opened the campus, invite companies to come here. We also want an R&D organization on our campus who organizes and orchestrates innovation with and between companies. And so, Whole Center came to be. In the first, say, 15 years of Holes, we've been very active in several areas. One of them, I think, some of the people who've been here for many BIDs may remember that Holes was very known of its work in OLED technology. And we worked with many great Japanese companies like Panasonic, Asahi Kasei, Mitsui, Sumitomo Chemical on the development of flexible AM OLED displays, which led to a success, and our technology was transferred to fabs in the US and Asia. And we moved on to other things. One of them is, for example, flexible electronics. The BID, 2 years ago, one of our spin-off companies had a nice presentation here, Traxon, who also here they commemorated the great collaboration with the Japanese ecosystem here, especially in the equipment industry, which they use to as a foundry for flexible electronics. And last but not least, we finalized the development of the health patch, which is now being commercialized by companies like Philips, but also our spin-off company Icon Health, also there in close collaboration with the Japanese companies, one of which was Shinetsu. And about, I say, 3-4 years ago, we started an endeavor together with our friends from University Eindhoven, Twente and Photon Delta in integrated photonics. And just you've been hammered with integrated photonics a few times, but I just want to inspire you again with the potential. It's been about 67 years already since the invention of the integrated circuit by Kilby and Noyce. And yes, it takes a time before an invention becomes really an innovation. You take now all these chips for granted, but it took a while to come to that place. And it was in the early 70s only, 50 years later, that the microprocessor by Intel was launched. And that really kick-started the whole evolution and led to the plethora of devices you have here. And it all was just by the simple fact, simple between brackets, by changing from discrete components like transistors, resistors, and capacitors into an integrated circuit on a wafer. Now think about that, 67 years, and what happened those into 67 years, and compare that to the potential of integrated photonics, where we're going to do the same, but not with electrical components, but with optical components. And yes, it takes a while because you heard about integrated photonics, but I want to show you in this presentation it's now really taking off, and I'm sure also my successors, Johan, will build on that. And one of the pipe cleaners, we call that for the development of integrated photonics, is of course the development and the rise of AI data centers. Have you heard about it? And I think that the big change came about 1.5 years ago when in the spring of 25, Jensen on stage said, if we want to scale AI data centers, we have to go to optical interconnects all the way. And that's been accelerating. And what you now see in AI data centers, the optical interconnects are there. They want to use it for almost everything, and you see a race to go to optical interconnects for transceivers, build transceivers based on optical chips. The switches have to go optical, which need optical chips, and so forth. And you see an enormous rise of the use of these chips. And my strong belief is this happens. This will happen. And we're convinced also part of that will happen in Europe and in the Netherlands. But it will lead to a very mature technology where you have scaled production, have mature production based on the needs of the vendors. And that will allow to go to a production level where the costs are going a lot lower, the maturity gets increased, and you can go to a lot of new applications next to AI. Now, as the PITC, which has already been introduced, I think, by a few of my predecessors in this nice BID, we want to help companies in that road. And we do that by offering, you can say, 2 tracks. One, to help scale the production from lab to pilot lines, and we'll show more about that later, mostly in indium phosphide, silicon nitride, and packaging. These are the 3 pillars in the Netherlands we have built our industry on. Next to that, we also want to advance the technology, and we do that by the shared R&D technology programs, already introduced by Takeshi-san nicely, and not only the technology, but also exploring new applications, and we'll show some examples of that, but also helping companies finalize their products so we can commercialize it. And I'll also show companies some examples of that here. But start with a nice example of an application we're heavily researching in Europe and setting up a pilot for that, is optical wireless communication. Unfortunately, the world has seen that RF can be jammed, intercepted, and there is a need for a secure data communication. Now, last year, together with companies like Airbus, FSO, and Signify, we shown at TNO that you can really build an optical end-to-end communication, starting with Li-Fi all the way to laser SATCOM to have communication around the globe, from small devices to the satellite. Another one was, just as a very recent one, announced by TNO and Airbus, that we now also can use optical communication between a flying airplane, cruising at cruising speed, and a geostationary satellite, 36,000 kilometers distant from each other, and with a laser with a bandwidth of 2.6 gigabits per second and 0 volts, we had a communication going. This is very impressive, and we're convinced this kind of optical will happen. And if you scale that and you want to also equip all kinds of airplanes and drones with it, you have to go to an optical chip, and we're working hard to do that. But it's not only for defense. There are many applications, one of which is if you go to autonomous vehicles, you have to offload the data, and also there, these kind of high bandwidth applications require optical communication. Another one is there are many companies now building all kinds of applications, AI data centers with optical chips, and we're helping them really mature the technology and coming with a full solution. And a lot of that is with packaging. In packaging, in optical chips is really different from electrical. You have to deal not only with the electrical interconnects, but also the optical interconnects. And that can be a very cumbersome way to finalize your device if you have an optical chip. And we're working with many companies on that, and it can do really fast prototype development. We can even do so low volume, and we now have experience with transferring our process flow to OSATs here in Asia. Based on the insights we gained from these product developments, we also now saw that, and you see that also in the electronic industry, a lot is going on with chiplet placement. You don't build a big chip from one die, but you use chiplets which you stack on top of each other, next to each other on an interposer. Same habits with optical chips. Here you see a nice picture of an indium phosphide photodetector we placed on a silicon waveguide. And you can do that also with very advanced pick-and-place. But we developed a technology called laser dye transfer, where you can do the same as maybe pick-and-place, but then 100 times faster, going to over 10,000 chiplets you can place per minute. Now, what about pilot lines? You heard about PICS Europe. It's one of the 5 pilot lines the European Union has funded in the European Chips Act. And it's all about advancing, setting up pilot lines around photonic integrated circuits. We call it a distributed pilot line because a photonic integrated circuit is not based on one material platform. You have several material platforms out there. We have indium phosphide, we'll talk about, which we are doing together with our partner companies. You have silicon nitride, aluminum oxide, and of course silicon photonics. And throughout Europe, you have different pilot lines in this area, including packaging, heterogeneous integration, test, and reliability. All in all, over 20 RTOs are involved over 11 countries with a total budget of 400 million. The one I'm talking about is the biggest pilot line we're building in Europe, and it's based on indium phosphide, where we go to 6-inch wafer size. Most production lines in the world at this moment are at 3 or 4 inch, and this will go to 6 inch at 10,000 wafers a year. That can equals to about 10 million complex photo ICs a year. It's going to be placed in a completely new building built by the high-tech campus. They will invest about 70 million into this. And it will have a state-of-the-art ISO 500 clean room, 1,650 square meters, and will be a fully automated state-of-the-art tool set. The thing we want to do there is not develop new process technology, but really show that we can scale from the current state-of-the-art 4-inch to 6-inch. So we're going to do this with focus not on new building blocks, but really on stability and reliability, so you can be sure that you can still scale the technology and become expert in this kind of technology. And why is already mentioned. This is because of the rise of AI data centers and really requiring millions and even billions of these chips. What's the timeline? Well, we've already started in 25 with the preparation. Together with our partners, we most notably Smart Photonics, we did the design, process equipment, ordered everything, and we're now in the building phase in 26, and it should be finished in 27, when we're going to install and hook up everything up, and then we'll go from there to improve and set up the process. Where are we now? This is a picture of, I think, about a week ago. The floor is there. It's going to be 4 stories high, and the first story is now being built. And you see the big cranes where everything is happening. We're very pleased about this. This is one of the. It's been a long time since in the Netherlands we built a semicon fab like this. So we're very keen to do this, and we have a nice webcam to follow the building process. And we don't do this alone. We do this with many companies around the world. On the pilot line, of course, we work heavily with Smart Photonics. They will tell more about their plans in scaling production. Of course, with the equipment vendors like ASML and Extron. And in the PITC share programs, we have many partners you see mentioned here. And this is also my call to action. We're here to help you advance your questions in integrated photonics, and we're open to help you out any way we can. For this, I thank you for your attention, and thank you.